Hello, AP Stats students, and welcome to day 3 of our virtual instruction for AP Statistics. I hope you got a chance to log in the last couple of days, got a chance to meet my colleague, Mr. Brendan Murphy. Him and myself will be taking you through some AP Statistics content and review over the next 5 weeks. My name is Luke Wilcox, and I'm an AP Statistics teacher in Kentwood, Michigan. And if you logged in yesterday, you know that I'm working real hard here to try and become YouTube famous. And that's so that my 8-year-old son will think that I'm a cool dad. So I did have a teacher reach out to me yesterday through Twitter, put on the hashtag YouTube famous. I showed it to my son, and you know what? He still doesn't think that I'm YouTube famous. So maybe we can work on that over the course of the next 5 weeks. So I'm going to jump right into things here, just to make sure, first of all, that you are in the correct place here. This is AP Statistics. I suppose this is 6th hour is the time slot that we have here. So hopefully you are in the right place. And I'm Mr. Luke Wilcox. I teach at East Kentwood High School in Kentwood, Michigan. Now, a couple of reminders, and I did go over these yesterday, but I just want to highlight these again today for any of you that are logging on for the first time today. We're going to split up these 5 weeks into a couple of different chunks. And the first chunk here, March 25th through April 3rd, we're going to be covering content that typically comes at the end of the AP Statistics course. And this is likely stuff that your teacher did not get a chance to get to before your schools were closed. So that's units 8 and 9. Today we're talking about chi-squared tests, unit 8. We'll get into unit 9 next week. But the most important thing about these 2 units here, that they are not going to be covered on your AP exam for the 2020 school year. Okay, this is just for you, optional if you want to learn it, to be able to take this on to college with you, but it will not be assessed on the AP exam this year. Well, then starting April 6th, that's when we're going to get serious about AP exam review. And we are going to go through the entire content of the course, or as best we can, within those 4 weeks there in order to prepare you for the AP exam. Now, for all of the lessons that you're going to see here, there are resources available that you can print out. And you'll see the link actually below in YouTube there. It's statsmedic.com/YouTube. And it's organized by date. So you just go there and you'll find today's date, March 27th. And you can go ahead and download the lesson and the homework problem for today. Now, another very important note here. I mentioned this yesterday at the very end of my lesson, but if you or someone you know, a student that you know, might need help with technology, they might need a device in order to take the AP exam. Maybe they don't have internet and they can't take the AP exam. Because the AP exam is going to be administered at home this year, we need to make sure that everybody has access to take that exam. So if somebody needs a device or needs internet access, we want to make sure that they can get that. So you see this web address here. If you could copy that down and send that to anybody that you think might need it in order to access a device or to be able to get internet access. Okay, so we are gonna actually go back to the homework problem from yesterday. So I posed this to you right at the end of the lesson, and let's just dig in and see how you did on this one. So I'm gonna start off by reading the question here. A study was conducted to determine where moose are found in a region containing a large burned area. A map of the study area was partitioned into the following 4 habitat types. 1, inside the burned area, not near the edge of the burned area. 2, inside the burned area, near the edge. 3, outside the burned area, near the edge, and 4, outside the burned area, not near the edge. The figure below shows these 4 habitat types. So we see the habitat types listed there, 1, 2, 3, 4, the proportion of the total acreage, and then the actual number of moose observed within those particular habitat types. And then it says the researchers who are conducting the study expect the number of moose observed in a habitat type to be proportional to the amount of acreage of that type of habitat. Are the data consistent with this expectation? Now, what they're saying here is that the researchers are looking back at these proportions and thinking that the number of moose observed should match those proportions according to the acreage there. So of course, this is going to be a chi-squared goodness of fit test. which is the lesson that we covered yesterday. And I'm asking you specifically for a couple of parts of the significance test here. In part A, it says calculate the expected count for the number of moose observed in each habitat type, assuming that the researcher's claim is true. Okay, so I'm actually going to just add on one more column here to my table, and this is where we're going to calculate our expected counts. All right, so let's just extend that table over, and let's think about how we would calculate those expected values. Okay, well, we know from yesterday that the formula for the expected values, we were to take the sample size n and multiply it by the proportion for that particular value of that particular category. Now we know our sample size here, we got 117 moose total in this sample, right? So that's our n. And then the p is just going to come from the proportion of the total acreage. So for habitat type number 1, we think 34% of the moose should be in that habitat type. So I'm going to multiply that by 34%, 0.34, and I get 39.78 as the expected value. Now moving into habitat type 2, we still have 117 as n, our sample size here, but now the proportion is 0.101. And I'm going to tell you that comes out as 11.817. And then the next two are going to be very similar in that we're going to take the sample size multiplied by the proportion. This one's going to be 12.168. And then for habitat type 4, 117 times 53.23. Oh, I'm sorry. Hold up. Back up here. Got to multiply that by the proportion, 0.455. And the answer is 53.235. Now, one way you can check to make sure all your calculations are correct is you can add up all those expected values, and they better add up to 117 or you made a mistake somewhere. Okay, so those are our expected values. And now we should be able to calculate our chi-squared test statistic. And just as a reminder, chi-squared test statistic, observed minus expected squared, all over the expected. We got all of our observed values here. We got all of our expected values here. It is now just a matter of plugging those into the formula. So our chi-squared value is going to be, I'm going to start with habitat type 1. So 25 was the observed, 39.78 was the expected. Plus, we'll go to habitat type 2, where we had 22 observed moose, where we expected 11.817. And then the third habitat type, we had 30 minus the expected 12.168. And the fourth, where we had 40 observed moose, and we expected 53.235. And you're going to have to put that whole mess into your calculator. And I'm going to give you the final answer here for chi-squared is about 43.7 as the chi-squared test statistic there. So hopefully you did all right on the homework problem there. And I think that we are ready to jump into the new lesson for today. And I'm going to start with the learning targets here. So much like yesterday, there are 3 of them. And I will make sure that at the end of the lesson today, we check back in with these learning targets to make sure that we got everything we needed to. So the first one is to state appropriate hypotheses for a chi-squared test. So that's about the null and the alternative hypotheses. The second one is to calculate expected counts and degrees of freedom. And this is going to look different than it did yesterday with the chi-squared goodness of fit. And then, of course, by the end of it, we need to be able to do a full 4-step significance test here. So we will definitely check back in on these learning targets at the end of the lesson today. So here is the lesson that we're going to be working through today, the activity. And this is available to download on statsmedic.com/YouTube. Or you could certainly just take notes in notebook paper, or you may just want to follow along with what I'm doing here. So I decided on a context that is very relevant right now, and that's about how we're doing this learning. And a lot of us are in a new situation here where you're having to learn online at home as opposed to learning at school with your teacher. So here's what the problem says. It says, do students prefer to learn at school, from home, or a combination of both, okay, which I'm calling hybrid. A researcher wonders if the responses would differ for high school and college students. A simple random sample of 40 high school students and a separate random sample of 60 college students gives the following survey results. And so we have the results of the survey. And I think we should pause right here and just take a quick look at the numbers and see if anything jumps out at us. And I had wondered about this too, because I felt like maybe college students were more used to online learning, or wasn't sure, but by looking at the results of the survey, I see that when we look at the students that preferred school, it definitely seems like the high school students preferred learning at school more than the college students, right? And so I do have, I would say, some evidence that the distribution of learning preference is going to be different between these two types of students, high school students and college students. We do have some evidence. The question is whether that could have happened purely by chance because these were just a couple of random samples. And of course, this is why we need a significance test to be able to answer that question. So we got a couple of warm-up questions here to just get us like sort of involved with the data. The first thing it says is how many samples are there and what populations are they from? Well, very clearly, if you look at the way that this is set up, there are two separate independent random samples here. So to answer that question, we definitely have two samples. Now, to think about the populations, well, the first sample here of 40 high school students is a random sample of all high school students. So I would say that the first population here is all high school students. And then of course, the second sample is a random sample of college students. So the second population here, I'm going to say is all college students. So I do want to just like note here that we have two different samples from two different populations. Whereas yesterday in the chi-squared goodness of fit, we only had one sample of Reese's Pieces from the population of Reese's Pieces. So that is one difference between the test from yesterday and the test for today. Now, question number 2 is asking about variables. How many variables are we measuring? Well, very clearly, if you look up at the data here, we are measuring the learning preference for each student. So that's certainly a variable. Now, some people might argue that type of student is a variable. But the reality is that type of student is the way that we're differentiating our two populations here. And we took separate random samples from each one of those populations. So when we went to our random sample of 40 high school students, we didn't have to ask them whether they were high school or college and record that as a variable. We knew that up front because we took a random sample of high school students. So this right here is in fact our only variable. And I do want to point out that it is a categorical variable with 3 possible categories of school, home, and hybrid. So I'm going to say that there is one categorical variable here. So we now have the biggest distinction between what we talked about yesterday in the chi-squared goodness of fit and what we're going to talk about today, which is the chi-squared test of homogeneity. And I'm going to just make note of this right now. For a chi-squared test of homogeneity, which is what we're dealing with here, you have 2 populations. And the reality is we actually could have 2 or more populations. If I wanted to take another random sample of, say, graduate level college students, I could do that. And we're going to be measuring one categorical variable here. Whereas yesterday we had 1 population, 1 variable. Okay, now we are ready to write some hypotheses for this here, all right? And remember, the null hypothesis generally says something like there is no difference. And in this case, we want to say that like the high school students are the same as the college students in terms of their learning preferences. So the null hypothesis is going to say that the distribution of learning preference is the same for high school and college students. And I do want to point out here a connection that, when we talk about things being the same, that's where the term homogeneous comes in. Homogeneous means the same. So you can see why this is called a chi-squared test of homogeneity. Now, the alternative hypothesis is going to say that something is different, right? We don't know whether it's the students that prefer school or home or hybrid, but some of those proportions are going to be different between these two populations. So we're going to say the distribution of learning preference is different between high school and college students. And in terms of homogeneity here, we are now saying that the two groups are not the same, not homogeneous. Okay, so let's move on to question number 4 here. And it says, now we will use a chi-squared test to determine if there is convincing evidence of a difference in the distribution of learning preference between high school and college students. Complete the table of expected counts. Okay, first just want to point out these values that we had in the table up here are the observed counts. And what we're looking for down here are the expected counts. And remember, the expected counts have to be calculated assuming the null hypothesis is true, which says that the distribution of learning preference is the same for high school and college students. That's going to help us figure out the values for these expected counts. So I'm going to start out with this expected value right here, just that one number, which would be the high school students who say that they preferred learning at school. And I want to talk about what we would do to find the expected value for that particular cell in the two-way table. So we are looking for the expected value for the high school student who says that they prefer learning at school. Okay, let's think about how we can calculate this expected value. If we assume the null hypothesis is true, then the distribution of learning preference is the same for this group as it is for this group. Well, I know based on the totals what that distribution should look like. It should be 30%, 20%, 50%, right? Because that's out of 100. So that's very easy. 20% should be those that prefer school, 30% should prefer home, and 50 that prefer hybrid for both groups of students, right? So in this first position here, we know 30% of those high school students would prefer school. So the calculation would be 30%, or I'm going to write that as 30 out of 100. 30% of all the high school students sampled. Well, we sampled 40 high school students, and 30% of those 40 high school students would tell me that we expect that 12 of them would say that they preferred school. So let's go ahead and write that in as our first expected value. Now let's go through a similar reasoning in order to get the expected value below that one. So now I'm looking for the expected number of high school students who say that they prefer learning at home. Well, if we look at prefer learning at home, it's 20% of the total, right? 20 out of 100. And so now I want 20% of my sample of 40 high school students. So I do 20% of 40. And I'm going to get a value of 8. So we have 8 expected high school students who say they prefer home. Now, I'm hoping now that we can actually generalize to a formula here for calculating the expected counts. So let's put this formula down here. If you're trying to get expected counts, when you have a table like this, which we call a two-way table, well, look at the calculations that we did above. 30 out of 100 times 40. Well, let's look at the 30. What is that? The 30 is the row total, right? And the 40, that's actually the column total. And then the 100, that's the what I call the grand total for the whole table. So it turns out that the formula for this is you take the row total for whatever row you're in, you multiply it by the column total for whatever column you're in, And then you take that whole thing and you divide it by what I call the grand total. Some people call that the table total. I like to call it the grand total. So we could actually use that formula for expected counts in order to find all the rest of the expected counts. I could go and find this one and this one and this one and this one, right? But there's a little bit of a shortcut here that I'm going to show you now. And the shortcut is this. Well, we've calculated 2 of the expected values already. The rest of them are going to be really, really easy from here. And here's the reason why. If I just look at the first row, which would be the row of those that prefer school, I know there has to be 30 total. And I know 12 of them come from the high school. Doesn't that mean that the other 18 have to come here? Just 30 subtract 12? And can I do that same thing in the next row? I know I have to have 20 total, and I already got 8 from high school. So that's telling me this expected count should be 12. Now we're left with 2 more here. And here's the trick on this one. Now I'm going to look at this column and realize that I have my 12 and my 8, but it has to add up to 40. So that means this value is going to have to be 20, right? So what we're realizing here is if we have all of the values in a row but 1, or all of the values in the column but 1, we can get that last one by just doing some subtraction. So this last one is going to be easy here. I know that one's going to have to be 30 in order to give me a total of 50 here and a total of 60 here. So something really important to point out here, the fact that we really only had to do 2 calculations here for expected counts, these 2. And all the rest of them, I would say essentially we got for free. So this is actually going to inform us about what's called the degrees of freedom for this significance test. And in this case, the degrees of freedom is 2, because we had to actually calculate those first 2 values. But once we knew the first 2, those had freedom to vary. But once we knew those first 2, all the other values were done for us, right? We could just fill those in. And it turns out that the formula that you use in order to get this degrees of freedom is you take the number of rows minus 1, right? Because if you have all the values in the row but 1, you can figure out that last one, and you multiply it by the number of columns minus 1, right? So in this case, if we were to use this formula, the number of rows in this case, we have 3 rows, right? 1, 2, 3. Don't use your total there. The total does not count as a row. So we have 3 rows. And the columns, we've got 1, 2 columns there. Don't use the totals column. And so 2 minus 1. And sure enough, you're going to end up with degrees of freedom 2. So I do want to just make a quick note here. Don't use the total row or total column, right? When you're counting the number of rows and the number of columns, you don't want to include those totals. Okay, so we now have all of our expected values, and it turns out that the significance test that we're about to do, the chi-squared test, it's going to look very, very similar to what we did yesterday with the chi-squared goodness of fit. Same formula, very similar calculations, find the p-value the same way. But I want to make sure that we know how to write that up in the full 4-step process here. So this is the same process that I used yesterday. We call it state, plan, do, and conclude. So let's jump right in. All right, starting with the state. Oops, we want to write our hypotheses here. So we've already talked about the hypotheses here. We know that the null hypothesis says that the distribution of learning preference is the same, right, homogeneous, for high school and college students. That's the statement that we have homogeneous populations. And the alternative is going to say that the distribution of learning preference is somehow different. And we don't know exactly which category it's going to be in, but we think that they're going to be different for high school students than it is for college students. Okay, so significance level, we actually weren't given a significance level here, and by default, we will go with the alpha level of 0.05 for our significance level. In terms of the name of the procedure, this is a chi-squared test of homogeneity. And we are now ready to check our conditions, and I hope these conditions look very similar to what we talked about in yesterday's lesson. We have 3 of them: the random condition, the 10% condition, and the large counts condition. So let me remind you of what each one of those says from yesterday. For the random condition, we need to make sure that we have random samples, actually 2 random samples that are independent here. So we're going to say that we have independent random samples of 40 high school and 60 college students. And remember, the reason why the random sample is important is because we want that sample to be representative of the population, because at the end, we'd like to make some sort of conclusion and generalize it to the population. In this case, we can generalize to the population of all high school students and all college students. Okay, 10% condition, remember, we only have to check that if we're sampling without replacement. And in this case, we were sampling without replacement. We didn't take one student out and then replace them back into the pool. And so we do have to check the 10% condition, and we have to check it twice, one for each sample. So for the high school students that we sampled, 40 has to be less than 10% the population of all high school students. Definitely a reasonable assumption because of the huge number of high school students in the country. And then for the college students, we sampled 60 of them, and we want that to be less than 10% of all college students. And I think both of these are very reasonable to assume. All right, now our large counts condition. This is where we check that all of our expected counts are greater than 5, but we need to make sure that we prove that we calculated those. And we did that on the previous page, but I'm actually going to just record each one of the expected counts. We had 12, 8, 20, 18, 12, and 30. And sure enough, all of those are greater than 5. All of those are greater than 5. Now, one quick note here, another way that you could justify the large counts condition, instead of having to list out every one of the expected values, you could just look for the smallest expected value. And in this case, the lowest expected value is 12. And if the lowest value is greater than 5, well, then of course, all of them are greater than 5. Just make sure you have those expected values somewhere on your paper. We had already done all the calculations of the expected values there. Okay, we are ready to do some work here, right? So this is where we're going to get into our calculations. We know our specific formula at this point. It's the same formula that we used yesterday for the chi-squared test statistic. O minus E squared all over E, and make sure you are summing all of those. Now we're going to have to do that for all 6 of our observed counts and expected values there. So this is going to be a little bit of a calculation. And I've got the numbers in front of me here. So I'm just taking numbers from back here. Of course, these ones are all of our observed values, and these ones down here are all of our expected values. So I'm going to start out in the top left, which is the high school students who chose school as their preference. The observed value was 18. The expected value was 12, all divided by 12. Then I'm going to move down the column there. So in my next cell, I have 6 minus 8 squared over 8. And then I have 16 minus 20 squared over 20. And then now I'm moving over to the next column. This is the college students now. And let's see, I've got 12 minus 18 squared over 18. And then I've got 14 minus 12 squared over 12. And then I've got 34 minus 30 squared over 30. So there are going to be 6 different parts to this chi-squared. We call these the 6 components for chi-squared, right? And I went through on the calculator and I found all of these values here. So let me show you what values I got for this. I got, let's see, my first value was 3, and then I got 0.5, and then I got 0.8, and then I got 2, and then I got 0.333, and then finally I got 0.533. And then I added all of those up. This is going to give us our chi-squared test statistic, which is about 7.17. So a little bit of work to do there, a little bit of calculation. Just give myself a little bit of room here. And let's go ahead and record that for our chi-squared test statistic, 7.17. Okay, now that we have our test statistic, we should be able to calculate our p-value. So let's go back to the picture up here. And we talked about the chi-squared distribution yesterday. This particular chi-squared distribution has 2 degrees of freedom. So it's actually going to look like this. This is a chi-squared distribution with degrees of freedom equal to 2. Remember, the chi-squared distribution starts at 0. You can't have a negative chi-squared value, and it is skewed to the right. And we got a chi-squared value of 7.17. Now, I don't know exactly where that is, but let's suppose that that chi-squared test statistic is somewhere right there. And we want to calculate to the right, always shading to the right, because those would be values more extreme. And this right here, the area of that is what we call the holy grail, people, the p-value, right? Now, I showed you 2 different ways yesterday on how to calculate the p-value. I'm going to remind you of that real quickly. The first way is to use table C. And table C is something that's provided on the AP exam along with your formulas. And the thing that you need to know in order to use this is the degrees of freedom. And we know that the degrees of freedom for this particular problem is 2. We had done that calculation. And what you're looking for now in the table is you're looking for your chi-squared test statistic, which for us was 7.17. So what you're going to do is you're going to go across the row for degrees of freedom 2 until you find your chi-squared value. Now I'm looking for 7.17, and I don't see it, but I do see 5.99, and I do see 7.38. And my chi-squared value would be somewhere between those 2. And so if you look above those where it says tail probability, this is exactly what we're looking for, is the tail probability. And what we know now is that the tail probability has to be between 0.025 and 0.05. So let's go back to the activity and let's record our p-value as between 0.025 and 0.05. Now, that'll be enough for us to actually write out our conclusion. I did show you yesterday how to do this on the calculator. So let me remind you of what we need to do on the calculator for this one in order to get the p-value. So if you could grab your calculator, or you can just follow along with what I'm going to show you here. But we want to find the area underneath the chi-squared distribution. And from yesterday, you should know that that's second vars. And the command that we want is chi-squared CDF. And the lower bound should be our chi-squared test statistic, 7.17. And you want to go out to infinity, 99999, degrees of freedom 2. And let's paste that onto the main screen there. And sure enough, we knew from table C that the p-value is going to be between 0.025 and 0.05. And we see, sure enough, it is. It's 0.028, I suppose, if we round it. So let's go ahead and jump back to the activity and let's put in this specific p-value that we just calculated, because I like that a lot better than the p-value that we get from table C. So I'm going to write in here that my actual p-value that we calculated from technology is equal to 0.028. And then I do try to get my students in the habit of putting a box around the p-value and putting a box around the test statistic. Those are 2 very important calculations that we need. And I think we are now ready to write a conclusion for our significance test based on that p-value. So much like yesterday, I am going to start with a sentence where I will interpret the Holy Grail, the p-value, and then we'll go ahead and actually make our conclusion. Okay, so to interpret the p-value, we have to start by acknowledging that we are starting with the null hypothesis. So assuming H null is true, and we've defined the null hypothesis up here, so I don't have to write it again. There is a, and then we need our p-value here, which is 0.028. And of course, that's a probability of getting chi-squared value. If you look back at our picture, we got a chi-squared value up here of 7.17. So a chi-squared of 7.17 or greater purely by chance. Now this probability is very low. It's very unlikely that this would happen purely by chance, assuming the null hypothesis is true. So that's going to allow us to make our conclusion here. So we're going to say because our p-value of 0.028 is less than our alpha level of 0.05, we are going to reject the null hypothesis. And we do have convincing evidence for the alternative. But we want to put the alternative in the context of the problem. So I'm actually just going to go back up here, remind myself of what the alternative hypothesis is saying. And essentially, I'm just going to copy that alternative hypothesis down at the end of my conclusion. We have convincing evidence that the distribution of learning preference is different for high school and college students. Okay, now we do have something that's statistically significant here. And I commented on this yesterday, that when you are doing a chi-squared test and you get a result that's statistically significant and you reject the null hypothesis, it's good to think about why that happened, right? So you can go back to your calculation to try and figure out, like, why is it that we got such a big value for chi-squared here, which led us to such a small p-value? And the best way to do that is to look at this part of the calculation right here, which is where we have each one of the components that contributed to the chi-squared test statistic. And you look for the biggest one. And so the biggest one here, I think, is our very first one right here, right, is 3. And let's look back at that calculation. What that was the high school students who said that they preferred learning at school. And it appears that the observed value was much higher than what the expected value was. And that's why we ended up with this pretty large component here. So this is what we call the follow-up analysis. And I would say, as part of the follow-up analysis here, I'm just going to tack this on to the end of the conclusion. I would say the observed number of high school students who preferred learning at school was much higher than expected. And I'll tell you that just warms my heart a little bit, that the high school students want to be at school, because I do too. So it makes sense to me that that would be the result. All right, we've got one last question here before we can summarize our learning. How is this test different than a chi-squared goodness of fit test? And this has to do with how many populations there are and how many variables. So let's just make note that this test, right, the chi-squared test of homogeneity, is for 2 or more populations, and you're going to be measuring one categorical variable. Whereas this goodness of fit test, which is what we did yesterday, has one population and one variable. Okay, so let's see if we can summarize everything that we learned in that activity in the important ideas. So we flip to the next page here. And this is where I'm going to tie it all back to the learning targets. We had 3 learning targets. Learning target number 1 had to do with the hypotheses. And I'm going to give you just sort of a general template that you can use when you're writing hypotheses for a chi-squared test of homogeneity. In general, it's going to say something like the distribution of, and then you're going to have to fill in the blank here. And what you're going to fill in the blank with is whatever is the categorical variable that you're measuring. For us, it was learning preference. And we're going to say in the null hypothesis that that distribution is the same, right, homogeneous, for, and then you're going to have two different populations here, or maybe more than two populations. So you're going to fill in the blanks here with population 1 and population 2. Okay, and then your alternative is essentially going to say the opposite here. The distribution of whatever your categorical variable is different for population 1 and population 2. You just have to fill in the blanks. Okay, learning target number 2 had to do with calculating expected counts and also being able to identify the degrees of freedom. And so we just have a couple of formulas here that we uncovered in the activity. First of all, the expected counts. Anytime you have data in a two-way table like this and you're doing a chi-squared test, you're going to use row total times the column total. And then you're going to divide by what I call the grand total or the table total. And then the other formula that we uncovered was the formula for degrees of freedom when you have a two-way table. It's just the number of rows minus 1 times the number of columns minus 1. And then the last learning target really was the 4-step significance test. And all I'm going to mention here in the important ideas is the big difference between the chi-squared goodness of fit test and the chi-squared test for homogeneity. And the chi-squared goodness of fit, which we did yesterday with the Reese's Pieces, we had one population, which was the Reese's Pieces, and we measured one variable, which was the color of those Reese's Pieces. Whereas today, chi-squared test of homogeneity, two populations, actually two or more populations, and one variable. Now, the last thing that I'd like to show you here is how you can do this whole significance test on your calculator. So if you want to grab your calculator, let's just see what this chi-squared test of homogeneity looks like on the calculator. So we still have our calculation there for the p-value, but listen, the calculator will do all of this mess for you, okay? Including getting some expected values. This is a really nice trick. So if you go to stat, and then you go over to tests, and you scroll all the way down, you're going to find eventually a chi-squared test. And you may have two of them. You may have a goodness of fit. Some calculators have it, some don't. But all of the calculators have this, the chi-squared test. Now, if you hit enter on that, what you're going to notice here is that the calculator wants you to do something in a matrix, matrix A and matrix B. So we have to go here to second matrix, right? This button and then this button. And we're going to have to go over and edit. And you may not have any values in here, but you want to create a matrix A. And you want the dimensions to be 3 by 2. And this is just going to be the observed values, right, from the activity. And so I already have those numbers copied in here. These are the observed values. So you'd go ahead and type those in. Then you could go back and actually perform your chi-squared test. So I'm going to go back to tests. I'm going to find the chi-squared test. And I've put the observed values in matrix A. Now you'll notice I didn't put anything in matrix B. You do not have to calculate your expected values. You only have to put in your observed values. And then you hit calculate. And sure enough, you get the chi-squared test statistic, which matches with what we got by hand, and the p-value, along with the degrees of freedom. And here's the really, really cool part about it. If you go back to those matrices and you go to edit matrix B, you will notice that these are all of your expected counts. And the calculator has actually figured that all out for you. You know, we did all that work to find these values. Turns out the calculator can do those for you. So it's a good way to check your work. So hopefully, you're able to use your calculator to check the work that you did in your on your significance test there. So listen, that brings us to the end of today. Now, there is a homework assignment. There's one problem. It's an old AP exam from 2016 that I'd like you to take a look at before Monday. On Monday, Brendan Murphy is going to be back with you, and he's going to talk about the chi-squared test for independence. And then I'll be back with you again on Tuesday. So I'm grateful for you tuning in today. And listen, I hope you enjoyed it. I hope you're helping me to become YouTube famous. If you liked this video, click the thumbs up and you thought it was good. I'd appreciate that. And I hope to see you again next Tuesday or next Monday with Mr. Murphy.